Thank you, Jan. Welcome, everyone. I have to share with you the fact that I have no competence at all and any matter about Antarctica so far. The closest I've been was the southmost point of Tasmania so far, but hopefully I'll improve over the next 6 years. But what I have competence in is the use of agent-based modeling to model first socio and environmental systems, and then use these models to interact with people who are part of these systems and eventually to solve problems associated with these systems. So I'll take you through a journey of a couple of projects we have been involved with over the last 15 years and more.
Pascal, somehow you're on mute there. I'm wondering if you can unmute yourself.
Yes, can you hear me now?
Yes.
Okay. So when we talk about modeling and modeling social and environmental systems, I'm not talking about plasma physics here. This is another debate. But when we have things and beings interacting, and we are, as modelers, the gods who decide what's in the model and what's not in the model, we have a high responsibility, and I'll try to share some of my thoughts about that. So the first one is that actual human ecosystems are often complicated, yes, but there was some time ago this general trend of describing all the systems as complex adaptive systems. The real systems are not complex adaptive systems. This is a way we modelers and scientists have decided to describe them. So we have to admit the fact that CAS models are just conveniently selected metaphors of these complicated real systems. And we have to be very serious about that. Otherwise, it's very hard to make a difference between pure evidence and evidence derived from models. From there, I derive the fact that modeling outputs belong to the end users and not the designers. And I'm happy to take questions on this one, because I won't have time to elaborate. Particularly true if models include management decision and social responses. And in these cases, collective design and social validations are highly recommended, as I will show you. So the first model, the first point I'd like to make in terms of modeling is that it's a tale of two cities, of two standpoints. And here I'm going to call my two best friends from when I was very young, Alice and Peter Pan. Peter Pan, as we all know, lives in Neverland. There's no dualism. Is Neverland is reality, even if it's coming from our world when he was very young. He's very confident, bordering with arrogant, and he's mostly happy through the whole story. So from a psychiatric perspective, this is a totally psychotic character. Whereas Alice, on the other side, lives in Wonderland most of the story. There's a strong dualism all around the story where she desperately tries to go back to the real world she belongs to, and she's trapped into this Wonderland. She's undermining herself most of the time along the story, and she's totally traumatized. Again, from a psychiatric perspective, this is a totally neurotic character. So as modelers, we have to decide whether we want to be psychotic or neurotic, whether we accept that the world out there is not exactly the way we design it in our models. And the way I've been doing this with the couple of teams I've been collaborating with over the last 20 years is always the same kind of structure. I'm not saying that we've been through all these steps all the time, but this is the philosophy of it. So you've got your real world at the top, and then first you try to design a domain model, and it can be just pen and paper, involving as many people as possible, and importantly enough, the people who have to be in the model one way or the other. Then you go into a conceptual model, which has to be transformed at one stage into an implementation model. So that's where you've got techniques like UML and other aspects of formalizing your models that comes into it. But the key here is that you have to design your conceptual model before you start even coding anything on your computer. Because then you've got the freedom to have different ways of using these models, whether a pure mathematical model programmed on your own computer, or whether you're going to design interactive simulation models using agent-based modeling, as I'm doing most of the time, as you can see on the left-hand side corner, or pure games, computer-assisted or not computer-assisted, just board games, in order to try to understand better this real world. And these interactive tools you're using at the implementation phase have to validate your model in terms of its connection with the real world you're modeling. So this is a loop we're going to go through the 3 examples I'm going to give you now. The first one, it was a long time ago when I looked at these slides. Oh my God, I produced that more than 15 years ago. So the model was called Catchscape. It was a model of irrigation systems in northern Thailand near Chiang Mai. And so going through this process I've just described, we had an empirical stage with a lot of ethnographers and anthropologists helping us to understand these systems in northern Thailand. Then we started designing a conceptual model with the people, with the main environmental component that needed to be there, the river, the paddy fields, the rain-fed fields, the forested areas, the villages, and so on and so forth. And then, and only then, we started implementing an agent-based model in this case of the systems and try to focus on what mattered. And in this case, because it was a conflict over irrigation and surface water, we wanted to focus on people and their interaction between each other and the interaction with the environment. This was a relatively complicated model for the time. Again, remember, it's 2003. And we've managed to stack a lot of different interaction in this model. Of course, we've got all the biophysical interaction you can think about, the land use, the soil types, the irrigation systems themselves, and the paddy fields. Each cell in the model has got a fully fleshed hydrodynamic model. And for the farmers, we know nearly everything about these farmers, their family, where they live, the plots they got, irrigated, non-irrigated, and so on and so forth. And that's the power of integration. Now, the power of ABM, why do I love agent-based modeling, is the fact that it was a very convenient tool at the time to transform something which was very realistic, like this GIS map of the catchment we were studying. And whereas the interaction between people and the environment and people with people correspond to the light green areas and the beige areas on that map. The rest is forested areas. People go there from time to time, but it's not essential. But it's essential, of course, for the hydrology of the catchment. So what we did, instead of trying to run the model on this GIS very realistic representation, well, we distorted the reality. And we created this very diagrammatic version of the catchment where we focus on the light green areas and the beige ones, which are the plots where people crop. You're going to say, well, in this case, your hydrological model is totally wrong. No, because it's a cellular automaton using ABM concepts. And each cell in the model knows exactly its own area, its surface area, which means that the hydrological model is still valid, while we can deal with very precise interaction within people when they start exchanging water. So that's the first strength of agent-based modeling. Try to focus on what you need. And finally, we move from integration to interaction. So we use this model or slightly simplified version of the model itself to interact with people, to really understand whether what we put in the model is really what they do and how they interact. Otherwise, we're playing God and we're creating a video game. We're not creating a scientific model. So it was the first pass, and we were quite happy. There was a couple of PhD students. And then I reflected upon all that. And a couple of years later, I had a second chance to have a crack at this approach. In this case, I moved to the Pacific, to the Republic of Kiribati, more specifically the atoll of Tarawa, for the one who had a chance to go there. It looks paradise from the plane, and as soon as you land, it's hell, total hell. 50,000 people living on literally a stamp. And most of the freshwater lenses have been polluted, and the few remaining ones at the time had to be pumped by the government to feed people on other parts of the atoll where there was no more source of drinkable water for these people. And of course, the landowners of these pristine areas still were not very happy with that process. So we were called in to try to understand the whole system, the environmental one and the social one, and try to find solutions for government and landowners to agree on something. So it's a pure conflict resolution approach. So again, empirical state, we try to understand the process on the left-hand side. Then we create a conceptual model. And the big thing here was to have a conceptual model which is realistic enough to represent the very, very complicated hydrogeological dynamics for freshwater lenses, and then represent this again in an agent-based modeling approach. And when you see the shape of the atoll, if we had again tried to represent the real shape of this atoll, the places where interaction matter are very small. So again, we distorted entirely the reality, but still keeping the proportions right. And again, we started integrating all these different components, the environmental ones, the surface of each island, the freshwater lenses, the land use, mainly coconut trees and some crops, the families living on these islands, and of course, the drinking water they needed, and the Public Utility Board, which is the agency in charge of providing drinking water to everyone. The beauty and the power of ABM, you know by now that I love ABM. It's the fact that sometimes mathematicians love to hate us, agent-based modelers, because hydrodynamics of freshwater lenses is very, very complex. You need a very sophisticated 3D numerical model to crack the code. In this case, we used an equation we found, which is a two-dimensional equation created by Volker for Tarawa many, many years ago. And we said, well, if we've got this equation, which is relatively simple now, let's try to create a three-dimensional version of it, and creating a upside down cup under each island, and couple of these cups if need be. And let's try to run the model like that. And it worked, and it was very simple, except that if you look at the bottom equation, bottom line of the equation, you've got a nasty x, which is the distance from the center, which gives you the difference of depth of the freshwater lens. And of course, if x equals 0, you cannot solve this equation. A pure mathematical model would store what we did with an agent-based model running on a cellular automaton. We said, okay, for this cell, don't calculate anything. This cell will look at the value of all the neighboring cells and get the average value. One line of code. And finally, from integration and the power of ABM, we go to interaction, and we ran workshops with the PUB, so the administration in charge of providing drinking water, the landowners on the other side, and try to find a common ground for them to agree on something. And here it was essential to put in the computer model things that people agreed upon from the start, and keeping in the game the things that were still conflictual. So for example, pollution through the toilet system, which is, let's say, less than optimal in Tarawa, was kept outside of the model because it was a very conflictual aspect that needed to be discussed in the game, not put in the model, otherwise the model would have been declared as totally wrong from the start by some of the stakeholders. Finally, the last example I'm going to give you, a bit closer to us, it was a World Bank funded project. I had the chance to roam the world looking at coral reefs around the world with my modeling team, which was very nice. And we started in Yucatan, in Mexico, with the Mesoamerican reef. So again, a lot of marine biology, a lot of socioeconomics, understanding of the coastline and the marine environment along the coast. We created a conceptual model, and then we implemented an agent-based model of this system. The model itself was very complicated because we were dealing with, collaborating with colleagues from marine biology who were adamant to have the most precise marine environment model as possible. Whereas on the socioeconomic side, we were more relaxed about the way we want to represent the dynamics and interactions. But nevertheless, the whole model was very, very complex. And that's where the power of ABM was paramount for us to achieve something that was meaningful. So you can see on the left-hand side here, we have a very rough representation of the coastline of the Yucatan. And for the one who have been there, the big patch in the middle, the green one, is the Siancan nature reserve, and Cozumel Island just up north of there. And you see, it's not very granular. Whereas the mathematical model we had for each patch of reef along the Mesoamerican reef was a differential equation model, very precise one with big fish, small fish, reefs, and algae. And each cell in the model had to run an optimization of this differential equation at every time step of the model. It was a massive undertaking, and we managed through an agent-based architecture this time to stitch everything together. So the socioeconomic dynamics on the coastline, the fishing vessels going out to sea, and even the pollution plumes coming from the tourism industry and tourism development along the coast. And finally, when we had that, we started creating simplified version of the model to engage with the communities. And because, as I said, it was not only in Mexico, but we went to the Philippines, we went to Zanzibar, and even Heron Island, we had to create different versions of the model. But the mathematical models themselves were very, very complicated and tricky to calibrate for each site. So what we did is to create simplified version even of the marine environment system, as long as it was still in the boundary of the master model, I would say. And that's where we started creating, as you can see in the little window on the left-hand side, the concept of shuttle model. So we had this massive ontology-based model that was the truth we all agreed upon. And then for each use case, we were detaching literally a shuttle that was a simplified version of this complex model in order to engage with a specific audience, with a specific community, with specific stakeholders. That was very, very brief, short, and I prefer to answer questions rather than boring you with other examples. So from there on, what would be the advantage for CEF program to use this kind of approach? Well, again, here I'm poking in the dark a little bit, and I hope I'm going to have some feedback. But in terms of objectives, these are the objectives you're going to find out with interactive modeling. Whether you want to share knowledge, that's the basic use of this kind of approach. Whether you try to solve conflict, I've showed you 2 examples of this, or as I did, and I don't have time to show it to you, we did when I was at CSIRO in Southeast Queensland, using this kind of approach as a flight simulator for managers. So you use these models for them to try things, try and fail and try again. The scales up to the community in the CEF program to tell me what's relevant. At micro level, we're already engaging with our colleagues from UOW on the moss beds in the dry valleys and looking at what our agent-based modeling could solve some of the issues we have in terms of micro modeling of all these issues we have there. At meso level, from early discussion during the preparation of the program, I think human environment dynamics around waste management around the stations is, I think, a clear target here. And even at macro level, we can think any kind of strategic negotiations around the Antarctica Treaty System. And that's it for me.